Welcome to the content material for Class 5 of Engineering Statics. You should be watching this video before your 5th class. In this lesson, we will cover the following topics. We will define what we mean when we say the right-hand rule. We will learn how to break up a force vector into its x, y, and z components using a 3D Cartesian system. And finally, we will learn how to compute resultant forces in 3 dimensions. In the previous class, we saw that we can break up a force vector into 2 Cartesian components along the x and y axes. Today, we will see how to do that if our force vector requires 3 dimensions. So if we're working in 3 dimensions, the first thing we have to do is define which direction the z-axis is going. From the xy plane, the z-axis could point up or it could point down. Throughout physics, the z-axis is defined using the right-hand rule. In the right-hand rule, we start with our right hand. Then we point our fingers in the direction of the x-axis. Then we curl our fingers back towards the arm. The thumb will point in the positive z-axis direction, just as is shown in this video. You can try it yourself. So now let's take a vector, A. We can break that vector A into components along the x, y, and z axes. And we can call those components of the vectors ax, ay, and az. And we can say that the vector A is the sum of the vector components ax, ay, and az. It's convenient for us to express this using unit vectors. If you remember last class, we defined the forces Fx and Fy using the unit vectors I hat and j hat. Well, we will add a third unit vector so that we can describe our vector in 3 dimensions. So if we have a vector A, we can describe that vector using the magnitude of the vector in the x direction. Ax times the unit vector in the x direction, which is I hat, plus the magnitude of the vector in the y direction, ay, times the unit vector in the y direction, j hat, plus our new z component. So the magnitude in the z direction, az, times the unit vector in the z direction, k hat. So we can now set up our equations. Alpha goes from the x-axis to the vector, beta goes from the y-axis to the vector, and gamma goes from the z-axis over to that vector A. So if you know these angles, alpha, beta, and gamma, then you can use the cosines of each angle to determine the ratio of the components of the magnitude. So for example, the cosine of alpha is equal to the ratio of the magnitude in the x direction, or ax, divided by the overall magnitude of the vector A, and so on. Alternatively, if you already know these ratios, then you can find the angles using the inverse cosine. So the inverse cosine of ax over A is equal to the angle alpha, and so on. We can express the direction of any force vector A as a unit vector. This unit vector, remember, has a length of 1. And we define the unit vector of A, this u sub A, using the I, j, and k unit vectors. We can also express a unit vector using the angles alpha, beta, and gamma, as shown. So if the unit vector has a length of 1, then we know that the square of the cosines, alpha plus beta plus gamma, will also equal 1. So we can take the square of the cosines of each of these and add it up equal to 1. And this can be useful if we only know 2 of the angles and we want to solve for the remaining third angle. For example, if we know alpha and beta, we can solve for gamma using this equation. The equations we looked at so far are helpful, but we don't always have those angles. Instead, sometimes we need to describe the vector's direction using 2 angles. Those angles are theta and phi. The angle theta is the same theta we looked at in 2D Cartesian vectors. You see here that theta is in the xy plane. The second angle, phi, is actually the same angle we called gamma. It is measured from the z-axis to the vector. Using these 2 angles, we can describe the direction of a vector A using this equation. So far, we have looked at several ways to decompose force vectors into the 3-dimensional Cartesian coordinates. The reason we do this is so that we can easily find the resultant forces of multiple forces acting in 3 dimensions. We will use the same principles that we used in 2 dimensions. So the resultant force R is equal to the sum of the forces A plus B. And we can find the resultant force R by adding up each of the x, y, and z component vectors. So the x components of the vectors A and B times the unit vector in the x direction, I hat, the y components for both A and B, and so on. So let's look at some examples to see how we can use these formulas. Okay, in our first example, we see that there is a single force, F, and it has a magnitude of 100 pounds, and we're asked to express that force using the Cartesian vector units, and also to find the coordinate direction angles of the force F. That means alpha, beta, and gamma. So here's what we need to find. We need to be able to find that force F using I, J, and K hat. And we're also looking to find alpha, beta, and gamma are. So let's start with what we know. Well, we can see that we know what the angle theta is. That's shown there, that angle in the xy plane. We can see that that is negative 45 degrees. In other words, it goes in the negative direction away from the x-axis. Positive would be towards the y-axis. So if we were to draw it looking down like this, x, y, we see that this angle is negative in the 45-degree direction. And we can also define the angle phi, which goes from the z-axis. So we see here that the force F here is 60 degrees. So we know that this is phi. So we know that phi is equal to 90 degrees minus the 60 degrees that we're told, or 30 degrees. So we can use our equation. We know that we can define F in terms of theta and phi. So we know that the x component is like that. This is the y component. And here we have the z component. At this point we can plug in our numbers. We know that F is 100 pounds. And we know that this is 30 degrees. And this is negative 45 degrees. And we have our z component here. This one is cosine 30 degrees, j hat. So finally we plug in our numbers, and I will use these brackets here because I want to use my units, which are pounds. So I find that if I compute this, it's 35.4. If I compute this, I get negative 35.4, and that's in the y direction. In the z direction, I find that this is 86.6, and we see that that's pounds. So here's our first answer describing that force F using our 3D Cartesian vectors components. And the last thing we have to do is find alpha, beta, and gamma. Well, we can use the inverse cosine. So we see that the inverse cosine, we know that alpha is equal to the ratios of these things. So that's what alpha is. Beta is equal to the inverse cosine for the y components. And gamma is equal to the inverse cosine of the z components. Well, so far we don't actually know what that magnitude f is. So we can use what we do know to find f first. And we already know that that equals 100 pounds, since we were told that actually. So we do that and we can confirm, if we plug our numbers in, we confirm that this adds up to 100 pounds, as we were told at the beginning. And next we go ahead and plug in our values. When we do that, we find that alpha is equal to 69.3 degrees, beta is equal to 110.7 degrees, and gamma is equal to 30 degrees. And that's it. Okay, in our second example, we again see that there's a single force, F, with a magnitude of 200 newtons. And again, we're asked to express this force using our Cartesian vector format. So what we're looking for in this case is a way to express that force vector F. Well, we're told some of the angles. We're told that beta is equal to 60 degrees, so the angle from the y-axis is 60 degrees, and we're told that gamma, or the angle from the z-axis, is 45 degrees. But we don't know what alpha is. Well, we can use the equation that says that cosine squared of alpha plus the square of the cosine for beta plus the square of the cosine of gamma, we know that that's equal to 1. So we can solve for cosine alpha. We know that cosine of alpha is equal to the square root of 1 minus the square of the cosine of beta minus the square of the cosine of gamma. Then we can plug those numbers in. When we do that, we find that cosine of alpha could be either equal to plus or minus 0.5. So let's see what the possible values of alpha could be. So if it's a positive 0.5, that means that alpha would be 60 degrees. Or if alpha is equal to, or the cosine is equal to negative 0.5, that means that alpha would be 120 degrees. Well, we see that alpha points in the positive x direction, and it does not go past the y-axis. In other words, if we look here at x and y, we know that it's pointing something in this direction. So alpha is less than 90 degrees. So we know that this option will not work for us. So we know the answer in this case is going to be alpha is equal to 60 degrees. So now that we have the three angles, alpha, beta, and gamma, we can now use those values to describe our force vector F using these Cartesian unit vectors. So we know that cosine of alpha for the x component, cosine of beta for the j, for the y and cosine of gamma in the z direction. And we plug in our values. We know that F is 200 newtons and when we solve each of those values, we see that we have 100, 100, and 141.4. Again, don't forget our units at the end. And so that's it for the second example in this class. So far, we have just looked at examples of taking a single force and breaking it up into its Cartesian components. But in this case, we have two forces, F1 and F2, that are acting on this ring, and we're asked to find the resultant force, which will be equal to the sum of those two forces. So what we're trying to find in this problem is that resultant force vector. I'll call that FR. And they also ask us to find the direction angles, alpha, beta, and gamma, of the resultant force. So I'll just call them alpha, beta, and gamma. So again, what we're going to do is we're going to start with the definition that that resultant force is equal to the sum of these two forces, which we know is equal to the same as the x components of that. So F1x plus F2x, F1y plus F2y, and F1z and F2z. So we have the x, y, and z components. Well, we have this information given to us. So we are told that F1 and F2 each have x, y, and z components as we're shown there. So at this point we could just plug that value in. So we see that the resultant force then is going to be 0 plus 50 in the x direction, 60 minus 100 in the y direction. So we see that F2 is minus 100 for its y component, and 80 from force 1, 100 from force 2, and our units in this case is pounds. We're told that it's pounds. So we just do that arithmetic and we find 50 minus 40 and 180. So this is our resultant force, and what we want to find is the magnitude of that. So we want to find the magnitude of that, actually, is what we're looking for. And the magnitude of that we know is the square root of the squares. FRX, FRY, and FRZ. So we plug in those values, 50 pounds, negative 40 pounds, and 180 pounds. And when we do that math, we find that it's 191. So here's the first answer. The magnitude of the resultant force is 191 pounds. That's what the magnitude of the force is of these two forces, 1 and 2, added together. The last thing we have to find is what is alpha, beta, and gamma. Well, we have the information we need for that. We know that cosine of alpha, again, is equal to the ratio of the x over the total. Cosine of beta is equal to the y over the total component. And cosine of gamma is equal to FRZ over F. And we solve. Plug in our values. Alpha is equal to the inverse cosine of 50 over 191. Beta is equal to the inverse cosine of minus 40. Don't forget that minus sign. and gamma is equal to the inverse cosine of 180. We solve, we find that alpha is equal to 74.8 degrees, beta is equal to 102 degrees, gamma is equal to 19.5 degrees, and that's what we're looking for. So that's it for the third example. Okay, in our fourth and final example, we see here that there are two forces acting here, F1 and F2. And we're asked to find what the magnitude of F2 would be so that the resultant force, Fr, acts along the positive y-axis and has a magnitude of 800 newtons. So in other words, we know that Fr will be equal to 800 newtons in the y-axis, which we use the j hat for. And we know that F1 has a magnitude of 300 newtons. And we're also given some information about the direction of F1. So we see that alpha, so the angle from the x-axis for that force 1, is equal to 45 degrees. We can draw this out. We know that F1, right, this is alpha 1 is equal to that 45 degrees. We also know that the angle from the y direction, y-axis, of F1 is equal to 60 degrees. And we're also given the beta, or the gamma, which is equal to 120 degrees. We're told all of that information. So alpha 1, beta 1, and gamma 1, we have information for all of those. Well, we also know that F1 plus F2 is equal to that resultant force. What we want to do now is we want to solve for F1. And since we have alpha, we have beta, and we have gamma. And so we can plug that information in. We know that the magnitude of it is 300 newtons, we're told that, and we plug in our information. Cosine of 60 degrees, and we have 120 degrees, and we can find that F1 has 212 newtons pointing in the x direction, 150 newtons in the y direction, and it's pointing in the downward direction, or negative z direction. At this point we can solve for F2, right? Because we've specified what Fr is going to be. We've specified, we know already what F1 is. So at this point we're going to solve for what F2 would be. So F2 we know is equal to Fr minus F1. And we can break up the individual components. So Frx minus F1x, Fry minus F1y, and Frz minus F1z. And we plug in the information that we have. There's no x direction for the resultant force because it only acts in the y direction. Same thing for the z, no z. And this is a minus minus, so that becomes a plus here. And all of this has units of newtons. And when we solve we find the value of F2. $650 here when we do the math, and again the 150. Now we want to find the magnitude of F2. Take the square root of the squares. F2y, F2z, each one of those squared. Plug those values in, and we find that F2 has a magnitude of 700 newtons. So I won't write it out. That's the 212, the 650. And now we have all the information that we need to find alpha, beta, and gamma of that F2. So now we know the magnitude is 700 newtons. We just need to know which direction it's pointing. So we'll go ahead and solve using the inverse cosine. And that's going to be equal to negative 212.1 over 700. It's the inverse cosine of that. And when we do that, we find that alpha 2 is equal to 107.6 degrees. Do the same thing for beta. Equal to the inverse cosine. And should be x there, sorry. F2y, it's a y, over F2. So we get our y value up here. We see that it's 650. 650 over the 700. Solve for that, we find that beta is equal to 21.8. And finally, we're going to solve for gamma. Again, the inverse cosine. Now we take the z component, plug in that value. Our z component was 150. So 150 over 700. Solve. We get 77.6. So we can write out our answers together here. Alpha is 107.6, beta 21.8, gamma 77.6, and we have our answer. And so that's it. So come ready on class number 5. We'll have a short quiz using 3D Cartesian vector components, and we'll see you then.